Hello, wonderful people! Here we are, the last day of class. How exciting! I'm going to take us through the second half of chapter 35 circuits here, and you will come away with knowing how the circuit breaker in your home works and what to do if things happen down there. Okay. There we go. Series and parallel. We talked about them last week. Let's show a picture. There's three light bulbs connected in series. So you can see light bulb number one, then two, then three, just like in the picture over here. And all the current goes through each light bulb in turn. Is that making sense for what a series circuit is? Okay. Then a parallel circuit. So that voltage coming out of the battery is felt across that light bulb and that light bulb and that light bulb. So they're all going to have the same brightness. And if you open the switch on one light bulb, the others stay on. Are we okay with this so far? Good, good. There's the very good cartoon talking about that. I'll include this in the posting. And then finally, schematics. These are the symbols that we use to represent things on paper. We're going to keep it simple. We're just going to do battery, switch, and a resistor. So there's the three light bulbs. Each one's represented by a resistor. There's the parallel circuit with three light bulbs and the three switches you can see in there. And that is a battery, the short and the long line, then the short line. Parallel circuits and overloading. Electric current is fed into a home by two wires called lines. 120 volts are on each of those two lines. These lines come into your house from outside the house. If you are in an apartment building, sometimes the lines come into your apartment from outside of the building, or sometimes the outside lines come into the basement of your building, and then your two lines come into your apartment from inside the building. There's a nice little picture of the way it works. The power station, where I've worked at a few, sends their high voltage to the substation that sends a voltage of thousands of volts, but not the hundreds of thousands of volts that are over here, to the transformer, which then takes it down to the 240 volts that enters your line. There's a positive 120 and a negative 120. Those two lines are coming to your house. There's a picture of a substation where it goes from hundreds of thousands of volts down to thousands of volts. Actually, I take that back. I don't see transformers there. This is just a switching yard. So it comes in here, goes through different switches, and then goes out through other switches there. Still a substation, though. What else? Oh, so here's the line, the power line, and it comes off there and goes into your house, down through there, and then into the basement. And also right there is the meter that the meter reader, can read. There's another picture showing the same things. Please note the wires on the top of the pole, those are the high voltage, hundreds or thousands of volts. Then it goes from there into the CAN, the pole mounted transformer, and that brings the voltage down to the secondary lines. And the secondary lines are that go into the house. And these big thick cables down here that are low, that's television, telephone, internet communication lines, not for power. There's a picture of the line coming in attached to the house. They want that nice and high so people can't reach it too easy. And then it usually goes into the basement where the breaker box is. So they bring those lines down through that little gray tube there. And this is a picture of the meter. Utility lines come in the top, and then what comes out the bottom goes to the house. Also, if you've ever had your electricity turned off at your house, if you haven't, lucky you, I've had it turned off over a dozen times over the course of my life. That's where they turn it off. They turn it off inside that box. And no, you can't just open up the box and turn it back on. Believe me, I tried. No, I didn't do that because trying would be breaking the law. So then on the other side of that wall, it comes in there. Oh, it's out of the picture, and it goes into the circuit board, into your. This is your breaker box, a breaker box in a typical home. So this up here shuts off power to the whole house. So if you open that breaker, everything in the house goes dark, and then this breaker goes to each of those individual breakers, and then those go out to individual rooms or things in the house, and the person has it labeled here. So the range, the stove, and the air conditioning, you see how that's two breakers that are connected by a little bar? That's because they work on 240 volts. And then everything else, the dryer is 240, but everything else is just one breaker. Even the refrigerator is only 120 volts. And so, yeah, that's if you look in your house, there's a panel that usually covers it. You can open up the panel and look inside and see this. There's nothing wrong with opening the panel. You can open the panel and see the breakers. That's not dangerous. Now, if it's a house where somebody does the work, sometimes they'll take that protective panel off and you'll see all the wires. See how this gray box, gray panel covers all that, and here it's removed. Now, that gray panel is supposed to be in place, and this is supposed to have a door that swings shut, but sometimes in a private homes, they'll take that off. I took mine off because I didn't have kids in the house, and I just like access. So when I needed to work on anything over here, I could just reach it. But if I did have kids in the house, especially if the garage was open, I just put that up in there and cover that. Also, I didn't take the door off. I'm surprised this person's a really bad slacker because you should still be able to have the door swing shut. And also, there's usually a lock on it, so you can lock it. Maybe not with a key, but at least so that somebody can't just swing it open. Okay. Parallel circuits and overloading. Each one of the breakers in the breaker box go to different parts of the house. Sometimes each room gets its own breaker, and sometimes different rooms share different breakers. It's not uncommon for one room to have two breakers controlling the electricity in it, sometimes three or more, like if you have put addition on the house or there have been previous problems. So just because a breaker says the upstairs bedroom doesn't always mean that opening that breaker turns off all the switches and outlets in that bedroom. So here is a picture. This goes to those two lines that would go down to the breaker in the basement, and this comes up to the room. And then you have a heater that is plugged in, a toaster is plugged in somewhere else, and a lamp is plugged in somewhere else. You can see that the heater takes 10 amps, the toaster 8 amps, and the lamp 2 amps, which is pretty typical, especially if that lamp has 2 or 3 bulbs in it. So consider a line connecting to a toaster that draws 8 lamps, a heater that draws 10 amps, and a lamp that draws 2 amps. If the toaster is operating, the total line current is 8 amps. When the heater is also operating, now the total line current increases to 18 amps. And if you turn on the lamp, the line current increases to 20 amps. So let me tell you this. Most breakers in the house, most of those breakers down there, and these breakers here, are set to 15 amps. So what happens if you try to put 18 amps through it? It's going to open. That breaker will pop open, and then all the power goes off. Now, some breakers, like this refrigerator down here, that is set to 20 amps. And the garage, I can see, is set to 20 amps. The kitchen circuit is set to 20 amps, both the kitchen circuits, which is kind of typical because those usually get some higher loads. But there's nothing set to bigger than 20 amps in a house 99% of the time. So if this is set for 20 amps, like it says there, oh no, 20 amps is the total coming through. Even if you have a 20 amp circuit breaker, this is going to pop it. If a breaker is rated at 20 amps, it will allow up to 20 amps, but at a current of 20 or more amps, it will trip the breaker, which opens and breaks the circuit. So if you plug those things in and you trip your breaker, then you can understand why. But what if things are just operating and it trips unexpectedly? Before you go down and just shut the breaker again, the cause of the overload should be determined and fixed. Insulation that separates the wires in a circuit can wear away and allows the wires to touch. This effectively shorts the path of the circuit and is called a short circuit. And a short circuit draws a dangerously large current because it bypasses the normal circuit resistance. So if you're unlucky to have a short circuit in the wires of the toaster, that can draw dozens of amps. And that's why this turns off at 15 amps, because a lot of amps makes the wires get hotter. And if you get too many amps going through it, they can get hot enough to burn. That's the whole reason why these breakers are all there in the first place. So this is not sparks coming out of there. This is a grinder wheel down here, and it's throwing sparks at this. But what are sparks? Tiny bits of metal. Is this dangerous? Throwing metal at a bunch of at an open plug and other things that are plugged in? Yes. Why was this dangerous? Well, look, they had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 things plugged into the circuit. Do you think it got to be? Well, I know what happened here. It was probably at 14 amps for the longest time, didn't trip the breaker, and then it got hot and got too hot because something in there was too old and wasn't working right. And then you get a small fire. Now, these small fires happen. I've seen 2 or 3 or 4 things like this over the course of my 51 years. And normally this happens when somebody's home because they're using these things. Okay, here's another thing that you don't do. This went to a heater. Heaters always take a lot of electricity because if you want to heat up a room, it takes a lot of power to do that. So when you plug the heater into here, the problem wasn't the plug itself. The plug, as you can see, is relatively fine. It was inside this extension cord that gave out, because these aren't designed to handle 12 amps going to a heater for hours and hours. So something in there got hot, it started to melt things, and eventually those melted things burned. And in fact, you can still see a little bit of fire going there from the electricity. Now, like I said, these little things happen, and usually they happen when people are home. But if they happen when you aren't home, or sometimes you get a little unlucky and the fire starts something else on fire, that's what happens. That fire was caused by an electrical outlet that got overheated and caught something on fire. It caught curtains on fire, and the curtains were next to the sofa. And before you knew it, there were a whole lot of flames in that house. There were people home. No, I'm sorry, they weren't home. This was called in by the neighbors across the street. So by the time they called the fire department, and the fire department, as you can see, I don't even think they're there yet. No, there's water being sprayed, and this looks like some water. But still, it was, by the time the neighbors noticed it, it was probably already in 1 or 2 rooms, and that's what happens. So every day, somewhere in America, houses burn down, and most of the time when house fires happen, it's because of electrical problems. Things like this, and this, and this, and this, putting too much load on a circuit. Okay, so if the circuit breaker pops and you don't know for sure why that happened, if you shut it and it doesn't pop, well, then go look around and see what might have caused it. And if you shut it and it pops a second time, well, then you have a serious problem. Okay, that's it. Good luck. And please answer the 4 or 5 homework questions. And please, I will post the questionnaire. Maybe we'll make that for Tuesday, just so I don't overload you. Sorry this took so long to get out. Okay, thank you so much. Bye-bye.